last few lectures we were examining the oscillatory flow in a pipe, unsteady, fully developed. Fully developed, that means that the velocity field is independent of the streamwise x direction. Unsteady, the velocity field does depend upon time, because the pressure gradient is a function of time. Okay. In this case, the pressure gradient is only a function of time, it does not depend upon position. As I had shown you earlier, the pressure variation in the r direction is 0, because there is no velocity in that direction and therefore no stresses. So, the pressure gradient in that direction is 0 in the radial direction. The pressure gradient in the axial direction, if you take the derivative of the axial momentum equation with respect to x, you will find that d square p by dx square is equal to 0. That means that dp by dx is only a function of time, okay, and in this case it was a sinusoidally varying perturbation. We had scaled r by the radius of the pipe, we had scaled t by the frequency, and we had scaled Vx by a viscous scale, and we got a dimensionless number Re omega, okay, which is rho omega r square by mu. Okay. And the way we had solved this is to write the velocity, okay, way we had solved this is to write the velocity Vx star, okay, is equal to the real part of V V tilde of r e power I t. Okay. E power I t, because we know that the frequency of oscillations is omega and the equation is linear. Therefore, the solution for the velocity should have the same frequency as the forcing function, okay, which is e power I t in this case, and therefore, the solution for the velocity also has to be e power I t. If we multiply e power I t by a function of r and takes its real part, we will get the actual velocity profile, where this thing, the v bar of r, satisfies the equation I r e omega v bar is equal to minus 1 plus 1 by r d by dr of r partial v bar by partial r. This is just to recall what was the equation that we had, and the boundary conditions were that v bar is equal to 0 at r star is equal to 1 at the wall, and partial v by partial r is equal to 0 at r is equal to 0. Okay. So, those were the equations and the boundary conditions. And we had got a solution for this v tilde, okay, multiplied by e power I t, take the real part, and we had a solution for the scaled velocity field. And I had shown you the nature of the solutions, okay, as the Reynolds number is changed from a low value 0.1 to a rather high value of 100. Okay. At low values, the velocity has a negative has a maximum magnitude in the negative x direction, when the pressure has a maximum magnitude in the positive x direction, okay, and it is nearly parabolic, and the velocity is opposite in direction to the pressure gradient. Okay. As it goes through the cycle, the velocity follows that same cycle. It is in phase, but negative of, that is out of phase by pi of the pressure gradient. In contrast, as the Reynolds number increases, the velocity actually has close to a 0 value when the pressure is a maximum, and it is a maximum when the pressure gradient passes through 0. Okay. And so, it has a very different characteristic. The other feature of this solution at high Reynolds number is that the variation is restricted to thin regions near the wall. The velocity is almost a constant in the bulk of the flow, okay, for r star less than about 0.6. And it was these features that we were trying to explain physically in the last lecture. Okay. So, first I told you R e omega was defined as rho omega r square by mu. It can also be defined as the ratio of two time scales. The viscous time scale, the time required for viscous diffusion across a distance comparable to the radius of the pipe, okay, where this viscous diffusion time is r square divided by the kinematic viscosity. Okay. Okay. And the second is the time period of the oscillation. Okay. The second is this time period of the oscillation. Okay. Okay. Now, if the viscous time scale is much smaller than the time period of the oscillation, that means that the Reynolds number is small compared to 1. And in that case, the steady the instantaneous profile will be the same as the steady profile for the instantaneous value of the pressure gradient. The reason is that momentum diffusion across the entire cross section is very fast. The time required for that is small compared to the period of the oscillation. Therefore, the velocity profile reaches its steady state value rapidly when compared to the time for the pressure to change. Therefore, you will get the same as the parabolic profile for that particular instantaneous value of the pressure. Okay. Okay. And that explains, okay, why this Vx is has this particular form, where Vx star is equal to minus cos t into 1 minus r star square by 4. The same velocity you would have got had you assumed a steady pressure gradient of magnitude cos t star. Okay. Of course, there is a small departure from this. Okay. It is not quite equal to 0 when the pressure gradient is 0. Okay. So, there are inertial effects, okay, even at low Reynolds number. Okay. And there are systematic ways in which we can take this inertial effects into account. Okay. So, I will go through the derivation of the systematic way for incorporating the inertial effects in the limit of low Reynolds number. Okay. The equation that I have, recall, is R e omega, okay, I R e omega times V tilde, okay, is equal to minus 1 plus 1 by R d by dr of R partial V tilde by partial R. Okay. That was the equation that we were trying to solve. Okay. And if this R e omega is small compared to 1, you can see that the left side is much smaller than the right side. Okay. If you neglect the left side altogether, you will end up with this parabolic profile. Okay. That is easy to solve. Okay. If you neglect the left side altogether, you will end up with this parabolic profile. How do we incorporate inertial effects in the limit of low Reynolds number? Okay. The way this is done is what is called a regular perturbation. Okay, analysis. Okay. So, I write V tilde is equal to V tilde 0 plus R e omega V tilde 1 plus R e omega square V tilde 2 plus etc. Okay. Note that the boundary conditions for the original problem are V tilde is equal to 0 at R star is equal to 1, dV by dr, the symmetry condition is equal to 0 at the axis R star is equal to 0. Okay. Those were the boundary conditions. So, I substitute that this expression, okay, this expansion, okay, into the governing equation, okay, and I will get I R e omega into V 0 plus there should be an R star here. So, yeah, this is correct. Okay, so, and in the limit R e omega being small, right, you would expect that the terms multiplied by R e omega power 1 will be much smaller than the terms multiplied by R e omega power 0. The terms multiplied by R e omega power 2 will be much smaller than those multiplied by R e omega power 1. Okay. Those multiplied by R e omega power 3 will be much smaller than those multiplied by R e omega power 2 and so on. Okay. So, therefore, I can equate the terms that are multiplied by R e omega power a common, okay, exponent. Okay. So, for the terms that are multiplied by R e omega power 0, okay, the equation on the left side is identically is equal to 0, because the largest term on the left side is multiplied by R e omega power 1. Okay. On the right side, I will have minus 1 by R d by. That is the terms that are multiplied by R e omega power 0. Okay. Similarly, what about the terms that are multiplied by R e omega power 1? Okay. On the left side, I have I times V 0. Okay. This first term here, I times this first term here is multiplied by R e omega power 1. Okay. On the right side, okay, this inhomogeneous term is just a constant. Okay. This inhomogeneous term is just a constant. It does not have any contributions proportional to R e omega square and so on. Okay. So, the contribution to R e omega power 1 from this inhomogeneous term is equal to 0. Okay. I do have a contribution to the second term due to this one. So, that is for okay. And then the next higher term, okay. On the left side, the coefficient of R e omega square is going to be equal to, okay, this term here, because there is an R e omega outside. Okay. So, therefore, I will get I V 1. Okay, and on the right side I will get 1 by R d by dr of R partial V 2 by partial R. Okay. That is what I get from this expansion. Okay. Of course, to solve these equations I also have to stipulate boundary conditions. Okay. And the boundary conditions are the coefficients of the boundary condition for V tilde. Okay. So, I can write this as V 0 plus Okay. So, those are the expansions of the boundary conditions. Okay. And the boundary conditions for each order of RE omega is the terms in that expansion for that particular order. Okay. So, this first one, the boundary conditions are V 0 is equal to 0 at R star is equal to 1 and d V 0 by dr is equal to 0 at R star is equal to 0. Okay. And similarly, you will get the boundary conditions for the higher order terms, they are all the same. Okay. So, V 1 is equal to 0 at R star is equal to 1, this should be at R star is equal to 1. Velocity is 0 at the wall at R star is equal to 1 and the velocity gradient dV 1 by dr is equal to 0 at R star is equal to 0. Okay. The next one will be V 2 is equal to 0 at R star is equal to 1. Okay. So, these are the equations and the boundary conditions that have to be solved. Okay. And you can see a pattern here. Okay. This first equation is an explicit equation for V 0. Okay. This is an explicit equation, second order differential equation for V 0 that can be solved in order to obtain the velocity profile. Okay. And you can easily verify this is identical to the equation that we had for a steady flow. Okay. As you would expect when you neglect inertial effects, you get the same equation as you had for a steady flow and V 0 will be equal to minus of 1 minus R star square by 4. Okay. That was the steady solution that we had. Okay. Okay. So, this is the steady solution minus of 1 minus R star square by 4. Okay. Now, once you have that solution for V 0, that turns out to be an inhomogeneous term in the equation for V 1. Okay. That turns out to be an inhomogeneous term in the equation for V 1 and therefore, I can substitute this in along with the boundary conditions to solve for V 1. Okay. And that solution, explicit solution for V 1 is equal to I into 1 no 3 minus 4 R star square plus R star power 4 by 64. Okay. That is the solution you would get if you substitute this expression for V 0 into the equation for V 1 and integrate subject to boundary conditions. Okay. Put the equation for V 1 into the equation for V 2 and then integrate subject to boundary conditions and you will get the solution for V 2. Okay. Is equal to 19 minus 27 R star square plus 9 R power 4 minus R power 6 divided by 2304. Okay. And you can continue this process. Okay. And then I can get the velocity Vx is equal to real of V 0 plus e power I t. Okay. So, I just substitute this in and I will get the solution. This turns out to be equal to minus of 1 minus R square cos of t by 4. Okay. This is the solution we had got in the limit of low Reynolds number. Okay. The next correction, you can see that there is an I over here multiplied by e power I t. The real part of that is going to be minus sin t. Okay. So, you get something that is minus r e omega into 3 minus 4 r square plus r power 4 by 64 sine of t. Okay. And then I multiply it by the next higher term, and that is a real term. So, I will get another function that is proportional to cos of t. Okay. So, I can include as many terms in the series that I want, okay, just by doing this step by step, and this gives us analytical solutions, okay, which we can understand easily. Okay. And if you plot this V x as a function of r, okay, this expansion for V x as a function of r, okay, it turns out that these solutions are indistinguishable from the numerical solutions for okay, r e omega is equal to 0.1 and even for r e omega equals 0.1. Okay. So, these are indistinguishable from the numerical solutions for these cases where r e omega is equal to 0.01 and even 0.1 and even for r e omega equals 1. It accurately captures the small shift in the velocity from the parabolic profile due to inertial effects. As I said, this expansion is okay, what is called a regular perturbation analysis. Okay. For a problem which has a small parameter, in this case the small parameter is r e omega. Okay. Regular because in the limit as the small parameter goes to 0, r e omega goes to 0, the solution that you get is the same solution that you would have got, okay, if you had set r e omega equals 0 in the original equation itself. So, if I solve the equation with a non-zero value of r e omega and then take the limit as r e omega goes to 0, I get the same solution I would have got had I set r e omega equals 0 in the equation itself. Okay. So, if I set r e omega equals 0 in the equation itself, then this is my reduced equation, okay, and the solution that I get is identical to what I would have got for a steady flow. Okay. So, that is what is called a regular perturbation expansion in the limit of small r e omega. Okay. So, this explains the parabolic nature of the velocity profiles as well as the departure from the parabolic nature in the limit of small r e omega, okay, and this works numerically well even for r e omega equals 0.1 up to r e omega equals 1. Okay. When the Reynolds number exceeds about 1, then there are differences between this and the numerical solution. So, that is one limiting case. In the limit of small r e omega, we know that the time scale for diffusion is much smaller than the time taken for the pressure to pressure gradient to change. Therefore, I should get a steady solution. That steady solution is for r e omega, the Reynolds number identically equal to 0. When the Reynolds number is small but non-zero, I can include the effects of the inertial term using a regular perturbation expansion. The opposite limit is the case where r e omega is large compared to 1. Yeah. So, in this case the equation has to be scaled again by the inertial terms. Okay. So, I will go back to the original equation, scale it by the inertial terms and then proceed. So, my original equation was rho times partial V x by partial t is equal to k cos of omega t plus mu This was the original equation, right, and I define as usual r star is equal to r by r and T star is equal to omega t, okay, and divide by k, okay, and divide the entire equation by k. Okay. So, I will get rho omega by k partial Vx by partial T star is equal to cos of t plus mu by r square. And now in the limit of high Reynolds number, I have to scale the equation so that the inertial term is comparable to the pressure term. The pressure term is cos t, it is order 1. Okay. Therefore, I have to scale the velocity by this term here. Okay. I have to scale the velocity by this term here and define, I will call it as Vx plus, okay, is equal to rho omega Vx by k. Or Vx is equal to k Vx plus by rho omega. And I substitute that into the equation, and what you will get is partial Vx plus by partial T star is equal to cos of T star plus mu by just doing the usual scaling. Okay. And this term is 1 over the Reynolds number. Rho omega r square by mu was the Reynolds number. So, therefore, I get a 1 over Reynolds number here. I get a 1 over the Reynolds number here. And then I have to write this as is equal to the real part of V tilde e power I t. Okay. So, if you do this substitution, you will get I times V tilde e power I t is equal to, my apologies here, there should be a negative in the pressure gradient which I had missed out. Okay. Therefore, this should be minus, okay, and this should also be have a negative sign. Okay. So, I get minus e power I t plus 1 by delta V tilde. Okay. Times e power I t. Okay. And this e power I t will cancel out, okay, in all terms. Okay. So, the equation now for this V tilde of r, I V tilde of r is equal to minus 1 plus 1 by r e omega and now these are total derivatives because this V tilde is only a function of r. Okay. So, and the boundary conditions are no slip at the wall and symmetry at the center. Okay. Okay. V tilde of r is equal to 0 at r equals 1 at the wall, and the derivative at r equals 0. Okay, so, those are the boundary conditions. Second order differential equation, two boundary conditions. Okay. If we now consider the limit r e omega much larger than 1, okay, you might simplistically expect that you can just neglect this term here, because it is multiplied by a small parameter. In the limit, as that parameter becomes smaller and smaller, you can just neglect that term. Okay. And then what do you get? Okay. I V tilde of r is equal to minus 1, which means that V tilde of r is equal to minus 1 by I, which, as I told you, is also equal to I itself. Okay. So, it just tells you that V tilde is a constant. This does satisfy the symmetry boundary condition at the center. Okay. But then there is no way to satisfy the boundary condition at the wall that the velocity is equal to 0, because there are no constants remaining in the equation. Okay. So, because of that, we cannot satisfy the 0 velocity boundary condition at the wall. Why is it that we cannot satisfy this boundary condition? Okay, think about it. We will continue this in the next lecture. I will see you then.